Hi everyone! In this video I want to explain a theory behind the diffuse lighting system I built in Touch Designer using spherical harmonics. Right now on the screen you can see a few examples of what this system could do. The main idea is that light is stored in a world space instead of being evaluated on a screen space only during the final rendering stage, as we usually do in Touch Designer and in many other systems. It means the same lighting information can be used for shading, for particle behaviors, or as a parameter for any other system in a scene. This video is a theory part. If you just want to use the system, there is a separate practical video where I go through all the components and I build scene from scratch. So if you're interested in practice, go ahead. And here I want to focus on the core idea of what spherical harmonics are, what this coefficient means, and why it works well for diffuse lighting. So let's start with a simple analogy. On the screen you can see three sine waves. Each one is a simple on its own. But when we add them together, it gets a more complicated curve. This is the basic idea of Fourier decomposition. Instead of storing the complex signals directly, we describe it as a weighted sum of a simpler basis function. Spherical harmonics works in the same spirit, but instead of decomposing the signal over time or in a line, we decompose the signal over the surface of a sphere. If we wanted to store incoming light from every direction directly, we could sample the whole sphere densely and store it as a directional texture. That would work, but also would be very heavy. And spherical harmonics give us a much more compact representation. We project this directional signal into a small set of spherical basis functions and store only the results in numbers as coefficients. Here's a visualization of those basic functions. Level 0 has just one function, it has no directional structure at all, it stores only average amount of incoming light. The level 1 adds three more functions, they start to encode directions, and they tell us where the main light gradient is coming from. Level 2 adds 5 more. These have more complex shapes and let us describe the incoming light much more accurately. So if we stop at level 2, that gives us 1 plus 3 plus 5, which is 9 coefficients. And this is the exact question I use in the system. You may have seen these shapes before in physics, where they are used to describe electronic orbitals. Same math, same family of functions, the difference here is just what we store in them. In our case, we're going to store incoming diffuse light. To make it less abstract, let's look in one coefficient from the first directional level. This function has a positive side and a negative side. Now I move a light source around it, and when light is mostly on the positive side, the coefficient becomes positive. When it moves to the negative side, the value becomes negative. And when the light is balanced between both sides, the value moves towards 0. So, one coefficient like this doesn't store the full image of the light. It stores only one directional measurement as a float. And when we combine several of these measurements together, we get a compact description of overall direction and the shape of incoming light. So, how many coefficients we actually need to keep in practice? Up to level 2, that gives us 9 coefficients per color channel. So for red, green, and blue, together it's 27 values per probe in the space. And here is a practical reason for stopping in level 2. For standard diffuse shading, level 2 already captures about 99.2% of useful lighting energy. That's also why 9 coefficients are usually enough for this job. Diffuse light is low frequency by nature. A rough matte surface blurs the incoming light, and the broad directional structure matters much more than the tiny details. Sharper reflections are different. If you want glossy, mirror-like behavior, you need higher orders and much more coefficients. But at that point, the performance advantage starts to shrink, so for the system it stops making any sense. That's why I'm stopping here in 27 coefficients. And there is One more practical limitation in my current version: it doesn't handle shadows or occlusion between the light source and the probe. So if there is a geometry between light source and the probe, the light is still accumulated instead of being blocked by this geometry. So level 2 is a good stopping point. It keeps data small, it stays fast, and for our specific task, it's accurate enough. Let's see what those 27 numbers actually mean in practice. Here I have high resolution environment map, and I want to use it as a diffuse light source. On one side, I render the geometry using the full environment map directly. On the other side, I first compress that lighting into spherical harmonics and then use only the resulting coefficients for shading. If you look at the faces of the geometry, the soft gradient, the color bands, the overall light direction are very close. And this is a key point. For diffuse light, most of the information that matters is in the low frequency part of the signal. So even though a full environment map contains the huge amount of data, for diffuse shading we can compress it down just for 27 numbers. And still the result will be the same, more or less. And here I can show this more directly. So this is full light in a state of a single probe, 27 coefficients in total. Now I block the spherical harmonics node. At this point, spherical harmonics light stop updating, the data is frozen, and when I remove the regular environment light from the scene, the normal version stops working because the environment light information is gone, but the spherical harmonic version is still visible because we locked the node and it doesn't need this false texture. Our 27 saved numbers are fine. And because the light is stored as a coefficient, we can also post processes afterwards. For example, we can rotate light field or shift its hue without going back to original environment map. But I'm going deeper into that in the modifier section of the practical video. Now, let's talk about how these coefficients are turned back into visible shading. To decode the stored light field, we need the coefficients themselves, and we also need the direction. In practice, the direction is usually the surface normal of geometry we want to shade. This is why the same probe can produce different shading for different surfaces. The stored lighting is the same, but the result depends on the way the surface is facing. Here I'm using the modified version of volumetric renderer from a Texture 3D operator family by Joseph Pels. With it, I can use a simple trick to make it easier to use. Instead of shading the real geometry with a real surface normal, I use the direction from the camera to each probe as an input direction for decoding. So the color you see in each part of the fog is a color that would be returned to the surface if there is if there is not a camera but a surface normal at this point. So as I move the camera, the direction changes across the whole volume, and the decoded color changes with it. It's not physical correct shading, of course, but it's just another way to visualize, and maybe it will help you to understand it better, the idea of decoding. In a real scene, a 3D grid of props covers the space where geometry lives, and during rendering, the surface samples the nearby probe and blends them and evaluate results, returning the color for the normal. That gives us special varying diffuse lighting across the scene using the data that's stored in the probes. The other big reason to use this approach is performance. Here I have a scene with a large number of small moving light sources. In a standard approach with FONGMAT, every shaded surface has to evaluate the contribution of every light source directly, and as this number grows, it becomes expensive very quickly. On my machine without spherical harmonics, performance starts to break somewhere around 4,000 or 5,000 active lights. Now I switch to spherical harmonic version, and instead of evaluating all these lights per surface, their contribution is first accumulated into the probe grid and then this geometry reads already compressed result from the probes. So the final shading step becomes much cheaper because it's no longer depends on evaluating thousands of individual lights. With spherical harmonics, the same thing can handle 7, 8, or 9,000 light sources with a stable frame rate. And if we also limit the influence radius of each light source, the performance scales even further. And this is a practical optimization idea because the small light source usually matters only within a certain distance away from the probe. So instead of evaluating every light at every probe, we introduce a cutoff distance and stop processing lights that's beyond this distance. In practice, this is a balance between the speed and lighting fidelity. How well it works depends on the chosen distance, on the light fall-off, and also on how many lights you have in a scene. And another important limitation in my current implementation is that probes do not know where they can see or cannot see the actual light source. In other words, the probe doesn't test visibility between itself and the light source. So this is the basic idea. We take a directional light signal over the sphere, represented with spherical harmonics up to level 2, and store 27 values per probe on a grid that covers the whole scene. That turns out to be enough for a pretty good approximation of diffuse lighting, and it also gives us much more scalable way to handle a lot of dynamic lights. In a practical video, I take all of this and turn it into actual Touch Designer workflow. The probe, grease, generator, calculators, modifiers, materials, and finally the full scene built from scratch. All the practical tools I use are available for free on my Patreon. And I hope this theory makes the settings of those components easier to understand and helps you to adapt spherical harmonics to your own practice. And I would love to see what you make with it. So, see you in a practical video.